Hello, guys. Long time no see. For half of you, I remember half of you.
Yeah, well, welcome back, man.
Yeah, I haven't joined this voice chat for like 3 months now, and I kind of surprised to see familiar faces. DJ, Relay, Criterion, Yoda. You renamed yourself and changed your profile picture, but I still recognize you. Uh, Boo, boo, boo. Yeah. Wait, Jesus Christ is God. Weren't you trolling yesterday?
No.
Okay, okay. So, I don't know if there is a point to discuss flat Earth here. Uh, what causes acceleration downwards?
We don't know. Do you know?
I mean, gravity, but even in the sense, even
No,
if it
no.
like
Gravity is just the effect. We're talking about the cause, what causes it. We both realize that things fall down, both you and I. We can drop something, it falls down. We're talking about the cause, not the effect, right? So do you know
uh,
what causes gravity?
some things fundamental, like electrostatic attractions, those weak and strong interactions between atoms. Like
Mm,
when you ask what is the cause, there is
The
no
cause.
cause. I mean, yeah,
There is a cause, but we don't know what it is. You can speculate that it's electromagnetism, for example, or mass attracting mass, or space time is bending. You can speculate about all those things. I'm just saying nobody knows. There is no theory that has been proven.
okay. But then we can see effects of gravity.
Yeah, we all see the effect of it. We can call that effect an effect of gravity, sure, but nobody
Right.
knows the cause of it.
That's pretty much like, how humanity, most of it, came to conclusion that Earth is like spherical, because like it's just kind of summation of effects that we can observe, not just
Well, I don't I don't agree on that because just my normal senses, if you were put on Earth and nobody told you you were on a ball, you would have immediately just thought, okay, look at the horizon, it looks flat. Okay. And do I feel any movement? No. All right, so we're stationary. You would never have come to the conclusion, oh, it must be a ball by yourself. Someone told you that, and then you started to believe it.
if
So
we
I don't
didn't have consciousness, we wouldn't know about it either way. So
Yeah, I mean, the default position, if you're honest, is that when you look at the horizon, it looks flat, and when you feel if you're moving, it feels like you're stationary. That is the default position. But
but there's a difference.
other than that, can I ask you a question? Are you
Yeah.
able to see the chat?
Yep, 1 second.
Yeah. Can you scroll up to the picture I posted on 21 minutes after the hour?
Yep, I see it.
What do you see there? You see that ball?
Let me yeah, I see the ball. Yeah.
Yeah, yeah,
Spirit
yeah.
of
What does it look kind of like the blue marble and other pictures that NASA has claimed that this is where you live? Does it look like those? You've seen
uh,
pictures from space before, right?
yeah, I'd say so.
Yeah, it
It's
looks
just
like
usually like to make this exact kind of picture of
mm,
Earth, the apparatus, like the camera, has to be from the side where sun is like lighting the Earth. Because if you think about it, there's only like small gap where you can take a picture like this, well, where full circle is visible, not like half of it, like moon. You know what I mean?
Yeah. But let's only focus on
Yeah,
the picture now. It looks like the Earth that people think they live on. You've seen these globes in classrooms and stuff as well, right?
yeah, pretty much. I can see even like reflection in the ocean if you can see it too.
All right, fine. But I want to ask you a question about the contents in that in on that ball. So the blue stuff, do you know what that is?
What do you mean on the picture? The blue stuff, you mean the
Yeah,
oceans?
it's oceans, water, right?
Yeah.
Do you notice something super weird about that water? It curves, right?
Oh yeah.
Yeah. So, and you would say that's because of gravity, right?
Um, I'd say so, yeah.
Yeah. So that's the official story. That's the lore of the ball, right? So now here's the problem. They have also told us the size. Earth's radius, do you know what that is? You can look at the picture. It actually says it right
Yeah.
there.
It's about 6,000 kilometers. Yeah.
Yeah, it's 3,959 miles, right? So that means we can use math to figure out how much water need to curve over distance. You with me?
Mm.
Yeah. So if we, for example, in the diagram, we look up 10 miles, you can see 10. How much drop over distance is that? 66 foot in the diagram, in the picture, right? So are you with me?
Mm.
So when we take a laser and we go to a 10-mile wide lake, there should be 66 foot of curvature over that distance if Earth is a ball. The problem is that when we shoot that laser from 1 foot over the water on one beach to the other side, it doesn't end up 66 foot in the air, which it has to be to do if Earth is a ball. It actually ends up 1 foot over water on the other side as well. So that means water doesn't curve. So that means we can totally disregard these so-called pictures from space because they do not represent reality. We cannot confirm it when we do measurements like these. And people have done thousands of these tests. There is,
Wait, so you come to a complete conclusion that it's not true just based on a single experiment, which like you conducted it, or
I
Why
have
not?
conducted,
You've come to a conclusion of photographs are true and correct without validating them.
yeah, I have done tests myself personally over 6 miles. And that was good enough for me. And I've also seen the beach in Denmark from the Swedish side. That's 10 miles away. And I have been able to see my brother on the 6 mile test that I did. So here's the thing: you don't have to trust me, right? There is Stark posted a video in the chat where someone did over 21 miles. They shot the laser 5 foot over the beach, 21 miles over to the other side, and it ended up 5 foot over the beach on that side as well. It should have ended up 266 foot in the air, but it didn't. So this
I
isn't
mean, for
one
me it
test.
worked.
Yeah, go.
So from about where I live or where I was supposed. Oh, I was not supposed to see. Uh, wait, France. Yeah, France is 180 kilometers from the point I could observe it.
Yeah, that's
Um,
about 110 miles. Yeah.
yeah, and I couldn't see it even though I was on the mountain and there is
Mm.
like a observation point. I think it's 42 meters above sea level.
Mm.
And I looked at the direction where France is, and I couldn't see no land and nothing
Yeah. Do you know why?
because Earth is curved, maybe.
Yeah, no, because we have something here called the atmo, right? There's air pollution, there's particles in the air, and so forth. Plus light doesn't travel for a lot for like forever either, and you don't have Superman vision. So that's probably just normal. Because there are other observations when we have better conditions, you can see mountains hundreds of miles away, right? So it just depends a little bit. Maybe you were there on a bad day, or maybe you can never see France from that spot. But I mean, there are so many other tests. Here's the thing, though. Even if you don't believe any of the laser tests that we posted here, it's so nice. You can still go out and find a lake that's 10 mile wide yourself and bring a friend and a good zoom camera and see if you can see him on the other side. So I just
10
showed you
mile?
the method. We only
Yeah.
teach people the method to do it themselves, right? So then you don't have to trust me. You can just trust yourself. And that's the easiest way to become a flat earther.
How to perfectly balance the laser? How to make it like perpendicular?
Yeah, you would have to do that, obviously.
Because if you think about it, if it's like 89.9 degrees, yeah, not 90, you know,
Mhm.
like that little difference over that large distance, it can affect maybe.
Excellent. So how about what we do, instead of trying to set it up perfectly horizontal, why don't we tilt it down? If you live on a ball, it will be pointing up anyways, and it's not going to make a difference. So instead of pointing it horizontal, we're going to point it negative. And then when we get to the other end, or maybe if we're lucky, here's another way you can do it. You can set your laser up and deliberately point it into the ground, and then you keep lifting it up until it just skims the ground.
Yeah,
And then go
that's
to the
a
other
good
end.
suggestion. As a
Yeah,
matter of
just
fact, that's what the guys in this test did. They shot it from 5 foot up, and it ended up 4 feet over the beach on the other side. So it was tilted down slightly. Good point, Matrix.
this is also another point. Okay, it doesn't matter if it's like set up perfectly straight. I mean, there's tests where they've gone to extreme effort to make sure it's perfectly straight using all sorts of leveling equipment, like the FE core test over 40 kilometers. But it really, you're probably going to have to do that if you wanted to hit the target on the other side. Otherwise you're going to have to move it around a bunch until you hit the target. But if the Earth's a globe, it doesn't matter if it's not perfectly straight, because there would be hundreds of feet of curvature blocking point A from point B. So you would not be able to hit your target no matter which way you point the laser. You can point the laser any way you want. If the Earth's a globe, over 40 kilometers or something like that, or even 10 miles, it's just 16 kilometers, you're not going to hit your target if the Earth's a globe. But every single test, the target gets hit. And these are done in all different weather conditions, all different locations. Frozen lakes, salt lakes, regular lakes, oceans, over all sorts of different places it's being done. It's hitting the target every single time. It's not possible on a globe.
Nice to hear you, by the way, DJ.
Yeah, you too, man. Good to see you back here.
Yeah. I remember you conducted lake experiments even twice in your life in Australia or something. Yeah.
Yeah, I probably did about 20, just because I lived at the lake. And, I lived like right next to the lake, and I had a boat, and I was using the lake quite a lot. I wasn't doing laser tests, but I was doing long distance observations.
Maybe we could or you could try laser test as well.
Yeah, I don't really need to at this point. There's been so many done. I mean, it's been done and dusted. I mean, when we've got a team of field engineers going out doing multiple different tests with a $30,000 laser and weather stations and like $30,000 worth of additional equipment, collimators, and all this crazy stuff, that's being done. We got PhDs like Dr. John D going out using all different spectrums of laser, and he's a professional in the field of optics, photospectrometry. I can't even say it. I forget how to say it. Photospectrometry or something like that. Anyway, he knows his stuff, and there's just so many tests that are being done. It's every single test shows that there's no curvature over these distances. And I just think it's weird that the globe side doesn't have any of these. They don't have any counter tests that show that, oh, look, it's a globe.
Wait, so you think a $1 laser wouldn't be like powerful enough?
It's good to use to, like, play with your cat or something like that.
Yeah, but not like over very long distances.
Nah, it's not really, man. It's not going to be any good. I mean, these people are using extremely high-powered lasers, big lasers. Even
Alright.
NATO was trying to find the geometric horizon. They did their own series of tests called the Sapphire tests, and even they were inconclusive on their test. They couldn't find the geometric horizon doing their own laser tests.
Over shorter distances, 10 miles isn't far enough for a mirror test to fail. You can actually do that if you can't afford a laser. And you can actually buy some lasers on Amazon that can shoot a few kilometers at least. But mirror test is a pretty good alternative because it's free.
Yeah, that's a great one. Also, I was watching a flashlight one the other day where he set up a pretty high-powered flashlight, and he had the camera guy 13 point something miles away, and the camera was only just above the surface of the water, I think 5 foot high, and you could clearly see the torch shining in the camera from over 13 miles away. And then he would say, oh, okay, put your hand over the front of the torch, and as soon as he would put his hand over the front of the torch, you couldn't see the light anymore. And they kept doing that, and then they kept lowering it. I think they lowered it all the way down to about 1 foot above the surface of the water, and you could still see the torchlight.
Yeah, I've done exactly that over 6 miles in Sweden. So I know that works.
But still, with lasers, I can put it into my mind how would you like perfectly make laser 90 degrees?
It doesn't need to be, but if you want to hit the target, you could keep moving it around until it hits the target, like keep adjusting it. But FE Core did that. They used all sorts of high-tech leveling equipment. So they put the laser on a big, long, extremely long device that they made. It took them months to create this crazy laser that they used. They spent $28,000 just on equipment, not including the time it took them. And they used like leveling equipment, like spirit levels and things like that, to make sure it was perfectly level. And because the target was the same height on the other side, they knew they had it correct because it hit the target 5 times in a row over different tests that were done up to 40 kilometers away. And they also used weather stations to account for refraction, light refraction. And yeah, they covered all bases when they did that test. Those tests. But yeah, even if you do one of these tests and it's not perfectly straight, it's still, there's no way the laser can go through the curvature of the Earth to hit the target. It's not possible for it to bend around that much and perfectly hit the target either.
By the way, Plane and Truth, when I like first joined here, you said that if you randomly like spawn on Earth, there is no way to like figure out whether like Earth is flat or not. It looks flat from the point you like spawn, for example. And you said that you don't feel the rotation like you would do if you move. But then that rotation kind of I mean it's different. I was about to say this immediately. It's just topic has shifted and we forgot. But I think it's important to mention that rotational motion, like you wouldn't feel that force because it's like so insignificant.
Yeah. So we could just grant you that, even though it's moving at 1,000 miles per hour, and then also right? Also orbiting around the sun at 66,000 miles per hour, which is a speed you can't comprehend because it's so fast. And
But
then
we're
it's
moving
also
together with it.
yeah, but the Earth is still moving at that speed, so it's moving, it's spinning at 1,000 miles per hour at the equator.
But it's not
And that,
accelerating. It's uniform
no,
motion.
it's not uniform motion, and constant uniform motion is constant acceleration. It's outward acceleration. So constant uniform motion is constant acceleration. And also it's not uniform at the same time. Yeah, it's like it doesn't do a perfect orbit. Okay, it's not doing perfect circles around the sun.
No, I mean, yeah,
It's also
I get,
tilting and wobbling. But this
yeah.
is the thing, it's moving at over 1.5 million miles per hour in all of these different vectors at the same time. Now, even though it's doing that, none of us can test whether you would feel that or not. Okay, so that doesn't really matter. We can say, okay, you wouldn't feel it, no problem. How do you know it's doing it then? What's your evidence for that? That's something that you would have to prove, because the default is that it's not moving, and the default is that it's flat. So if you wanted to prove that it's curving, you're going to have to prove that the water's curving over distance. And if it's moving, that's another problem. You guys need to be able to prove that it is actually moving empirically. Like, so yeah.
Oh, fair enough. Yeah. But still, about that subjective feeling, it's not like on a roller coaster you're doing 5 spins in a second. It's like you're doing 1 spin in a year, if you mean around the sun. Around Earth's axis, it's just once a day. So it's like really slow, relatively.
Except that what we actually observe is the sun doing a cycle across the sky above the Earth, and we don't see the Earth doing a cycle around the sun. You see the difference?
What do you mean?
What we actually observe, everybody from the ground, the Earth, everybody standing on the same ground, right? Different positions across the world. We observe the sun moving across the sky in daily, weekly, monthly, and a yearly cycle. That's what we see. That's what we observe. What we don't
Yeah, but
see is the Earth doing that. Like the Earth in motion, going around the sun. Nobody sees that. Nobody observes that. That's just on
there is
drawings,
a way,
cartoons,
like for
written
example,
stories.
I'm like a little bit into like stars and that kind of stuff. And since November, I was like monitoring Jupiter before it became popular. And before it was bright dot, it was actually very dim, but I saw its position relative to stars around. And like every week, I noticed it becomes brighter and it moves relatively. So if you keep tracking that, like the relative position, it's definitely not star, because if you use telescope, you see more dots, you see Jupiter more like clearly, and you can like track that
Yeah,
you're
just like
kind of
the other
moving.
stars, Jupiter, there, it's not like a regular star. Jupiter will be so-called wandering star. It's like you're looking at a different gear of the sky, because we have the stars doing this circular motion, or we observe the stars kind of like doing their own motion, but then Jupiter, as a wandering star, is almost in its own gear,
But it's not emitting
and it
light.
has a cycle. Jupiter, like all the others, has its own cycle, and
But
cycles are
Jupiter
repeats.
is not a star; it's a planet.
Yeah, it's called a wandering star. Planet, meaning the word planet, wandering star.
Okay, I've never heard that
It's a
someone
wonder.
calling her like that. Sorry, so you confused me.
Well, yeah, it's like many of the other lights in the sky. Jupiter has similarities to the luminary, to the other stars or wandering stars, right? They have similarities. What they have is a different pattern as they move across the sky.
Oh, and also like notice that relative position of sun. Like if you were to imagine it like you're on a sphere and sun goes kind of behind horizon and goes down, 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 down,
Just
down.
imagine it like you're not in a sphere.
But then when you look at the sky and where there is Jupiter, you kind of realize that it's like opposite side to where sun is like right now underground, for example, on the opposite side. So it's like illuminating Jupiter.
That's you mentally adding that in. You're saying, oh, I see the sun, but I don't see Jupiter because it's at the other side of the world, under the ground that I'm standing, or the sun is below the ground and I see Jupiter. That's
Wait. So how high do you think the sun is?
that will be an unknown for me because I cannot measure it. There might be some people that have estimates about that, but the one
I mean,
that
if
the
Earth
sun,
is
even for
flat,
the sun, even for the globers, is in an apparent position. So something apparent,
if
it's
Earth
you
were
cannot
flat,
triangulate
it
it
would be
until the
very easy
distance.
to measure using
Ver-
triangles and angles of because it's a single source of light, and you can because
Yeah,
Earth
but it's
is
apparent.
Stark posted a couple of good videos in the chat. You should have a look, Marian. One of them is the sun analemma, which kind of, to me, proves that it's the sun that's moving and not us, because otherwise the Earth would have to do an eight-shaped thing underneath the sun, and we know it doesn't do that just on account of feeling that we're not moving, right? But the
Exactly.
sun,
wait.
the sun doesn't
I'm not
exactly
following
break
up.
down either.
I lost the thought. What do you mean eight shape? I mean east always remains east and west always remains west.
Have a look at the video. You will see that that shows us the sun analemma. You would have to Google it if you haven't heard of it before, but it does a figure 8 over us.
What does?
The sun.
The sun?
That doesn't work if the Earth is a
Okay.
ball.
Sun.
Look at the video in the chat.
I'm googling it.
The sun is moving. Posted by
Is
Stark.
it recent? Oh yeah, I see
Analemma.
it. Sorry.
Yeah. So you would have to argue that the Earth is moving underneath the sun in that pattern, and that becomes really weird when it's if Earth
Wait,
is a
where is it?
ball. I mean, it's in the chat. There's a video 56 minutes after the hour, posted by Stark. Shadow angles prove the sun
Is
is
it the
moving.
same? Wait, so it's not the same day. It's
This is over a
February,
year.
January. Over a year, right?
Yeah, it does that pattern
So
over and over.
but if Earth had a tilted axis, wouldn't it have like the very same like thing?
Dude, that's what you will have to argue, that the Earth is actually doing that pattern underneath the sun every year.
The sun that we see in the sky is apparent to each different person. Okay, if you were to draw a straight line from what your eyes looking at the sun, and other people also drew straight lines from their eyes to the sun, they're not all going to meet at a single point. Everyone sees it unique to themselves. You're not going to have convergence of all of those imaginary lines of people looking at the sun. The sun is very much apparent. We need to take personal perspective and field of view and angles and all sorts of things into account, and also the atmosphere, the atmo. All of these things need to be taken into account when we're looking at an apparent light in the sky.
So the sun is moving, not the Earth.
Correct. Just like we all
Obviously.
experience. Yeah.
Obviously.
So where does so if okay if okay one part of the world is at like a day, another is at night, and the opposite, right?
Yeah.
But we can make it like a claim that if at least one half is illuminated, right, then the sun must be at all times in kind of space above the plane of Earth.
Yeah, it's always above the Earth, but because it's not 93 million miles away, as it moves to different sections of the Earth, the light from the sun isn't able to push forever through the air. It's called the attenuation of light. Okay,
But
so as
it doesn't look to me like it's moving away. Actually, I mean, the sun is not becoming smaller, or it's not slowing down when
no, it's
like a
not
plane.
close enough. It's not close enough that it would get smaller. It changes a little tiny bit in size, but
But it's
not
not
much at
slowing
all.
down. That would work on any scale.
No, it wouldn't. It wouldn't slow down either. You're seeing it within your field of view. Okay, you can see in a big hemispheric field of vision above your head, just like if you see a plane coming from the horizon. Okay, and the plane looks like it's going up into the air, even though that's just perspective, and it takes a big arc over the top of your head, and then it does the same thing as it goes away in the distance the other way. Right, the plane's at the same altitude the whole time, except it looks like it's converging. I mean, it looks like it's coming up from a convergence point due to perspective. The same thing happens with the clouds or a hallway, right? Or when you're at the beach and you're
But
looking out at the horizon.
for a plane, okay, you said that it wouldn't work about size for a sun, but for plane at least, while it's above you, it's moving, for example, yeah, slow but fast enough. But the far it goes to the horizon, it kind of looks slower because there is like not infinitely, but you know what I mean, um, more space than just right up, be above your head. Yeah, so uh, it looks like from the perspective it's slowing down, not slowing down, but it's moving away slower, even though it can move with the same speed, for example. But with sun, it kind of sets with the same kind of movement speed as like it's constant throughout all flight.
No, it's definitely not. It's definitely not. Sometimes I think even according to the globe model, it slows down quite a lot as it reaches towards the horizon, some places more than others. But you're looking at an apparent light that's only appearing to go down due to the way your perspective works. Now, there's a lot of mystery when it comes to the sun, and you're only looking at an apparent light source when you're looking at the sun. But it's not going to behave exactly like the plane because the plane's obviously much closer in your field of view.
But guys, I think if we take like a time lapse of a day, like of the sun during the day, and we do sections and like measure like the lengths or whatever, uh, this like the speed of the sun throughout the day is just the same, even though it's perspective and it should be changing.
No, it does change. It's just apparent change though. And also have a look at what Stark posted in the side chat.
Yep.
The one of the time lapse of the sun. I mean, to me that just looks like the sun is moving away. Okay, and that's what we would expect to see due to the way that our perspective works.
In the horizon, it looks the
It's just
sun is
there's
being
clouds there.
no because with no clouds, the light in the camera it appears larger, so it looks closer. It's just like a visual illusions. There are
Yeah. No, I'm not saying it's shrinking as it's moving away. It's just appearing to shrink because of the
yeah, it's appearing to shrink because there's
because of the
less light and it can
yeah
focus.
it's not glare. There's another word for it. I forget what it is, but it's just it's exciting the sensor of the camera and it's making it appear like it's bigger. That's not what I'm saying. What I'm saying is the sun looks like it's just moving away from you due to perspective, the same as when a plane moves away from you or when the clouds converge with the horizon or when anything goes off in the distance. It looks like it converges into what's called a vanishing point. It's just human perspective, the way we see things. It looks like the sun's moving. That's my main point here. It doesn't. Okay, so you would have to claim that you're on a globe and you're spinning backwards away from the sun faster than the speed of sound, blah, blah, blah. We just say the sun's moving across the sky, and then we could go down to that water there and we could perform all sorts of different tests, and the curvature that would have to be there isn't there. So it can't be a globe.
Wait, what did you say about speed of sound?
Well, okay, so the Earth is spinning faster than the speed of sound. So you're spinning backwards. Okay, so this is what they say if you're on a globe and you watch a sunset. Okay, they say the sun is not moving from your perspective, and
Jesus Christ, sun is exploding on that GIF. It's not you sending, sorry. In the chat.
Yeah. So this is what they tell you if you live on a globe. Okay, so the flat earther says the sun's moving away from you. It's going east to west, the sun's moving. On a globe, they say, no, the sun's not moving from your perspective. They say you're actually spinning backwards away from the sun faster than the speed of sound, faster than a 9mm bullet. And that's what makes it appear like the sun's setting.
I don't see a problem with that. If momentum is conserved and air moves together with the Earth, so relatively nothing moves. Everything is stationary.
How does the air move with the Earth?
Momentum?
Gravity is not the answer. That's not what they claim.
I mean, when you're born, it doesn't mean you like born with zero momentum and you like
Yeah, you are.
Born into like a space.
No, you're just born onto a flat Earth, and then you get told it's a globe when you go to school, and then you believe it's a globe just because you got told it's a globe, even though you don't experience a globe. Okay, and this is the thing. That's not my point, whether you would feel it or not. That's not what we're talking about right now. We're talking about the sun moving across the sky. We just say the sun's moving across the sky because that's what we experience. And then you guys say that you're spinning backwards away from the sun.
Right.
That's all.
No, it's just you say like subjective what you see, yeah, subjective perspective and how you like perceive it as flat Earth. But then I feel the same way, but I like see on the sky like we're on the globe, you know?
Yeah, but you wouldn't think that if you weren't taught that while you were growing up. You just see the sun moving across the sky. That's okay. So this is you see the sun moving across the sky. I see the sun moving across the sky. You imagine in your head, right, that really the sun's not moving across the sky. You're just spinning away from the sun. Okay, and this you go to the ocean or a lake and you see flat water, but you've been told that no, really that water's curving. Okay, all of these things you get told, they've basically replaced your common sense with a whole bunch of nonsense, and you just believe it blindly.
How can it not work opposite way, you know? That like you
because there's no evidence. There's no evidence for it.
Oh, okay. You linked observations with evidence. Okay, I got this. I just thought for a moment we like shifted from the evidence more to like observations that we can see, not measurements, but yeah.
Yeah, I didn't post anything.
So like in terms of observations, like what we see is like it just can work in opposite way. Like flat earthers, they see sun moving away, like sun is moving, not the earth, for example, spinning. Because it's harder to imagine 3D than linear movement of the sun in a way.
Yeah. Look, that's all. Like, we all see the sun moving across the sky. Okay, we can't detect any motion. You already admitted that. You said you wouldn't detect any motion. So you experience a stationary Earth. You already admitted that.
No, wait, you can.
Okay, how?
Not with the feelings, subjective feelings, because if you use like
not
formulas,
subjective. There's nothing subjective about whether you would feel the motion of the Earth or not. You already said you don't feel the motion because it's going so slow
You
over
don't
such
feel
a
it
long
because
period.
86,000 seconds
Yeah.
a day.
So, okay,
Yes.
so we can agree that we experience the Earth as motionless. Right? You just said that. That's what you just said. But when I tell you, when you have to actually say it out loud like this,
Because
all of a sudden you
physics
hesitate.
say- No. I'm hesitating because I just saw that like physics tells us that gravity has no limits. I mean, those distant galaxies, they do affect us gravitationally, just a little tiny bit.
Cool
But
story. What's that got to do with whether you would feel motion or not?
but it wouldn't, because
Nothing.
feeling motion for a human.
Okay,
it
so you
has to
don't
be-
feel the motion, so you experience the Earth as with no motion, stationary. Say yes.
You can say you experience no subjective
So why
force
is
on
it
your life.
subjective? Why is it subjective? You don't feel any motion. You said you would,
Because
even
you
if it
can-
was a
you
globe.
cannot-
Even if it was a globe, you wouldn't feel any motion. So when I say, do you experience the Earth with no motion?
No,
You should
humans
easily
at
be
the
able to say
time-
yes, but for some reason you're hesitating because now you're
No,
thinking,
this-
you're thinking
look,
about
look,
it. This is funny that globe earthers do this, right? You'll say that the Earth's so big and we're so small that you can't see any curvature.
First
And then we
foremost,
say,
English
hold
is
on
not my
a
first
second. Hold on, let
language.
me finish. English, you're very good at English. Don't be silly. Okay, so
But it's not
when
my first.
okay, well, you're doing great. Good job. Congratulations. So when we ask globe
Thank you.
earthers, how come we don't see the curvature? They say, oh, the Earth's so big, but we're so small, so we can't see any curvature. And then we'll say, so you experience the Earth as flat. And they'll be like, well, actually, well, and they can't just say that. It's like their brain won't let them say it. It's the same thing with the motion. It's the same thing with the movement of the sun. It's like a cognitive dissidence thing or something like that. It's like you're not admitting you're a flat earther just because you say what you just admitted a bunch of times. You don't feel any motion. Could still be a globe, but you don't feel any motion, so you experience the Earth as motionless.
Okay, now can I say?
Yeah, go ahead.
So you say you don't feel any motion, but you are born the way to not feel the pressure of 100 kilopascals. You're born the way to not feel the gravity of 10 meters per second, which is like crazy acceleration downwards that we can actually measure. Like if you drop a pen from your ceiling to 2 meters, and then you like rearrange formula,
They say gravity is an extremely weak force. That's what they say. It's an extremely weak
like
force.
comparing to the
Even just
Boltzmann
electrostatic, even just the electrostatic force is like 10 to the 39 power stronger than gravity. So they say gravity is an extremely weak force on the globe model. That's what they say. But this is the problem with the gravity. We can just debunk that really easily by showing you that the water's not curving. Okay, so if you have a downward acceleration of 9.81 meters per second squared, that means all of the water on the Earth would have to be curving at that specific rate that we can calculate based off the radius. And if it's not curving, then gravity's not working. It doesn't work. You don't have gravity, you don't have a globe if you don't have the curvature. It's as simple as that.
So it all comes down to the thing that you don't see the curvature of like water, basically, because even the sun
Well, you
observation.
would see
the link-
byproducts. You would see byproducts of the curvature. Okay, so things in the distance would start to become hidden behind the curvature at a certain distance. It would have to be hidden.
Isn't that what we see?
No, it's not what we see. In fact, what we see is that we can see orders of magnitude further than you would be able to see on a globe consistently. And there's no evidence, right, that there is actually any curvature. Sometimes we can have physical obstruction, like ocean swells, which are waves out in the ocean, causing the bottom of something to be obstructed, or we can have miraging effects, such as sinking, which makes something look like it's essentially sinking or hidden behind the horizon, even though it's not. It's just an optical effect, an atmo effect. but these things can be replicated on flat surfaces on a small scale. So we can prove that it's not actually due to curvature. But most of the time, when we do long distance observations and laser tests, the curvature that would have to be there, it's never there. There's not one test that shows that the curvature is there.
Okay, I get this claim. It's just
this is it.
There might be
this is
no
it.
need to like repeat some claims many times.
Yeah, because you guys don't seem to get it, and it's fine. I understand it. If you want to cling onto the globe, you guys have to try to divert to something else. But if you don't have curvature over the water, which covers 70% of the globe, then you don't have a globe. It's just as simple as that. Everything's going to lead back to the prerequisites of the globe. Okay, it's like, okay, if you want to have a globe, this, you have to have this. Okay, that's the curvature.
Wait, so
That's
what's
the main
like
thing?
the main problem for like flat earthers that they're facing is trying to measure the curvature of water.
No, it's
You
not a
are
problem.
fake news.
It's actually not a problem. It's the easiest thing to do, and we've got thousands of tests. I could sit here for the next 10 hours going over test after test after test. And when I ask a globe earther to present a test, they don't have one. There aren't any.
I mean, they probably don't come here with kind of a goal to change your minds, guys. So
No. That's not about, like, we have people.
That's a side story.
Yeah, look, we have all sorts of people come in here. We've got people that hate flat Earth and that literally spend their whole life trying to debunk flat Earth. We've got physicists that come in here, all sorts of people, engineers. None of them have any of these tests, and we're not even asking for people's personal tests. Find one test from anyone throughout all of history. Go on ChatGPT, go on Grok, go on Google. Find one. There aren't any.
I think wait, for curvature of water particularly, yeah, just by sending how it's called like the weather balloon, because it can go quite high, and you can like if you can find some like checkpoints maybe and measure probably the not the angle, wait, yeah, the angle. If Earth is curved, it would make sense that angle was smaller for the city you're observing from afar.
Yeah, we've done these things. We've taken infrared cameras worth $15,000 up on planes and been able to see things that are 1,000 miles away that should have been hidden behind miles of curvature. So when we go up higher, we can actually see further because there's less air, there's less disturbance. And then if we use an infrared camera, we can see even further. So there's a bunch of people that do, they go up on planes to 30,000, 40,000 feet, and they take all their camera equipment up, and they're able to see things that are 500 miles away, 700 miles away, 1,000 miles away, that should be way below the curvature of the Earth. Not to mention they're also seeing a completely flat horizon as well. And then when we send up weather balloons, we just see a flat horizon once again as well.
Okay.
Yeah.
But ultimately, what's the idea behind it? You think, like, for you, how do you feel? Is it you believe that you like understand the world how it is, and all the others are like manipulated by governments of every country in the world, or like how do you see it?
I see it as it's kind of like the globe's kind of like a tradition. It's like a hand-me-down type of thing. The people that are teaching you that it's a globe in university and school, they're not lying to you. They believe it's a globe themselves because they were also taught it was a globe, and the people that taught them it was a globe got taught it was a globe, and so on, right? And you're going to try to trace this back, and it's going to go back to crazy people like Pythagoras and that kind of thing. But most people that believe it's a globe, they don't really ever question it. They get taught it from such a young age and then it gets reinforced throughout their life. They don't know anything about it. 99% of the globe earthers that come in here, they don't know the radius. They don't know like the drop over distance rate. They don't know the basics, right? They just believe it. They're just believers. It's just like a faith that they have because that's what they got told. They've never questioned it. There's nothing wrong with that, right? They've never had additional options presented to them. They're just, they're just believing. And they've never heard the flat earth arguments before. They've never seen the tests. And so they've not gone and tested the earth. And they've just been told the same things that you're saying. It's like, oh, it's too big to see the curve. We're too small to feel the motion. Don't worry about it, guys. We got it all covered. Just trust the science.
Yeah, I mean, personally, most of us wouldn't be able, like, maybe if they try hard enough, they would be able to measure the curve. But if I was personally checking for the Earth being flat or spherical, I would probably rely on even like sun, stars, and that kind of stuff. Even though you guys saying that's all just light, we don't know nothing about, and that kind of stuff. But on the southern hemisphere, you see one set of stars, which they kind of loop. So if you go, if you know what I mean, you can build a map which is spherical of all stars.
Yeah, I know. Look, I know that there's two apparent points of rotation in the sky with the stars. But what you don't realize is how the globe became to be a thing in the first place. Okay, so they took the motion of the stars, the apparent motion of the stars, okay, and they put that into a conceptual model, which became the celestial sphere. Okay, and they turned that into a coordinate system. And then over time, they inverted that coordinate system that's based off the sky, off the stars, and then they inverted that and turned it into a globe. That's where the globe came from. It came from observing the sky, and it came from an imaginary / conceptual way of observing the sky.
I think it kind of came more from like a logic, because there are 3 laws of logic that make like every single statement like logically true or like false. I think the first one is about congruency. So you specifically define something, like you don't diverge from the term you initially used. And then second law of logic is contradiction, that there couldn't be contradiction. And the third one is eliminating of the middle. So it's either this or not. So
no, that's not how it came to become a thing in the first place.
So
actually, the first people that were saying that the Earth were a globe were people like Pythagoras, okay, who was like a mystic cult leader. Okay, the cult of Pythagoras. I'm not sure if you looked into that, but he's the first person. Yeah, he's the first person that said that the Earth's a globe, apparently, in history. And it wasn't because he went out and made observations or did measurements. Okay, it was through crazy philosophical reasoning, because he thought that he basically thought a sphere was like a divine shape. Okay, and that the creator must have made the Earth a sphere because it's the most perfect shape. They kind of worshipped spheres. He thought the universe was like a musical instrument, and that the planets like gave out tune songs and things like that. All sorts of crazy stuff if you look into Pythagoras. Okay, and this is the kind of place that the globe came from. Later people took Pythagoras' ideas and kind of ran with them as well. So long before the Earth was even conceptualized to be a globe, the ancients would envision the way that we see the stars as like a big celestial sphere. So before the Earth was even presented to be a globe by anyone, they had a celestial sphere. Okay, and it's like an imaginary way of conceptualizing the motion of the stars in the sky. Okay, and then over time, that celestial sphere got inverted into a terrestrial sphere, and that's the spherical coordinate system that we still use to this day. It's an inverted celestial sphere. It's just based off the way that we observe the sky. It's got nothing to do with people going out using logic or anything like that. There's no logic behind it. What's logical is...
I was following up from that, especially after you said about two rotating, how you said it, star
celestial poles.
Yes, celestial poles.
Or, not even celestial poles. Let's call them apparent points of rotation that the little lights in the sky appear to sort of go around.
So there's a polar star that shows you direction to the north. That what we call north. Yeah. So if there is one and only one, it makes logical sense that the Earth would be like flat. But because there are two, something is going on, and
there isn't two. I mean, what you're talking about is Polaris. Okay, and all they did was just say you're standing with Polaris directly above your head.
No,
okay, you could call that 90 degrees. And then you're just moving away from it, okay? And due to perspective, it's going to get lower and lower in the sky. And you're just plotting out points on the Earth to where you're measuring a certain angle to Polaris. Okay, when you get to around to where they call the equator, which is also in the sky, okay, that's where you can't see Polaris anymore. So then they just invert, right, duplicate that for the south. It's just a spherical coordinate system based off the way that we view the sky. There's a whole bunch of inconsistencies with it. It's not like that's where compasses even point. If they're pointing north, they're not pointing to directly under Polaris. Like the magnetic field doesn't even match up with the claimed globe at all.
Yeah, but I don't see a problem with that.
Okay, well, you're going to find the problems, the water's not curving.
Okay, let's maybe we should like...
It's always going to come back to that, man. Like you can make assumptions all you like about envisioning the way that the sky works. Okay, we all observe the same sky. All of the ancient cultures, every single ancient culture all over the earth had the same idea that we're in.
I get it. With all respect, really. It's just like you said, it always comes to that water thing. That
it does.
Like,
it does. It sucks for you guys. I know it's hard. It's rough. It's tough being a glober when you just have flat water everywhere. You guys have to use mental gymnastics and try to divert the conversation into things that none of us can truly validate.
No, sometimes it feels like you catching people on the claims, like about the motion. You remember you tried me to say
What motion?
Like you tried me to admit that we don't feel any...
You said that. This was your claim. You said you wouldn't feel any motion. So I said, okay, so you experienced the Earth as motionless, right? And you couldn't say that you would. This was your claim.
Yeah, that was my claim, because it's like we don't feel that negligible stuff. We don't even feel the pressure, which is actually very high, and we would feel if we like
What do you
go
mean you don't
underwater.
feel pressure?
The pressure that is like at ground level, so 100 kilopascals. If you go underwater, you feel it.
It's not pushing you down. It's not pushing you down, though. It's going. The gas particles are moving in all directions.
Yeah, but your body doesn't feel it. It's just comfortable with it. So you feel different when you go high in the mountain.
That's because it's a light medium. It's gas particles. You can't even see them.
Yeah, I know,
like,
but
it's like the lightest. It's like the lightest medium possible. It's just gas, and the gas particles are just moving at random in all directions. The gas particles aren't going down. I mean, they are going down, but they're also going every single other direction equally.
They're pushing on you.
No, they're not push. What do you mean they're pushing on you, though? Like they're bouncing off you.
No, I mean all the particles that are above you, they literally push 100,000 newtons per meter
They're
squared
not
of your body.
pushing. Okay. All right, and to have gas, as far as we can test in a lab, okay, on a smaller scale, is that to even have gas pressure in the first place, you need to have a contained system. It's even in the definition of gas pressure. It's the necessary antecedent to have gas pressure is to have a container.
The earth, the ground, is the wall.
No. It's above the
the
ground. Yeah, that's
It
that's
No, what do
says
you
one
mean?
more.
What do you mean container?
yeah. A container doesn't just have one wall. You don't have. Okay,
No,
if you want to
well,
have so if you want to have pressure that's higher than the atmospheric pressure, like 14.7 psi, if you want to have any pressure that's higher than that, you need to have a container like a basketball or something like that. Okay, you can't just have the pressure on the outside of the basketball. You can't pump the outside of the basketball up to higher than atmospheric pressure, obviously.
or
Okay,
you could go to
you
the
need to have
core
an
of the earth.
enclosed container to have pressure.
What about going underwater?
That's
Because
different. We're talking about gas right now.
there is no container for like water.
You need to have a container to have a body of water in the first place. It's a different thing, though. You're just changing the topic. We're talking about gases needing a container. Okay, water's another thing that also needs a container as well. You can't have water on the outside of a basketball.
But how is it different? I mean, we measure the same kind of density gradient. The deeper you go underwater, and the deeper you go, I mean, the difference between like mountain height and then ground level. We also measure the difference in density of air.
Yeah, but it's not the same thing. It's a completely different thing.
Why so?
Because with the water, right? The water is just dependent on the amount of water that's above you. Okay, you could have like a 10-foot
What's
tube
the
of
problem
water
with the
that's
gas?
huh?
So what's the problem with the gas?
Water, because
What's the
gas particles move at random in all directions. Okay, water droplets or
What?
water doesn't do that. Okay, this is
No.
the difference
Why
between
did you say?
gases and liquids and solids.
What do you mean they move all in random directions? It's not that they're flying against 10 meters squared
Yeah,
accelerated downwards.
a gas particle will just move in a straight line unless it bounces off another gas particle or off the wall of its container. If you look up right now, what is the definition of gas particle movement? It'll just say gas particles move at random in all directions.
Yes, but every particle, like no matter the size, is getting accelerated just like all the other particles. Like because every
No,
cell.
No,
gas particles only move, they move because of kinetic energy, which is caused by heat temperature.
Right, and where is infinite kinetic energy coming from accelerating our bodies downwards?
There's nothing's accelerating our bodies downwards.
No, we accelerate downwards. What makes us accelerate downwards?
Nobody
It's like,
knows. Nobody knows why
but that's
there's two
infinite
primary
energy.
directions. There's two primary directions, up and down. Okay?
So the kinetic
Nobody
energy
knows why
is
down is
infinite.
down and why up is up. But you're more dense than the air surrounding you. Okay, and you need to use energy to keep yourself from falling down and sinking through the air to the ground. If you were a helium balloon, you would just float up into the sky. You'd go up if you were a helium balloon. But if you're a rock or a human or something like that, you're going to sink down through the air because the air can't support you because it's extremely light.
Wait, so you making conclusions about the physics of gas just based on
No, this
the
is
definition?
mainstream. This is just mainstream gas laws. It's ideal gas law. Like you can
What do you
look
mean?
any of this up. This is all how universities teach it and explain it and describe it and define it. This isn't a
I
flat Earth.
don't
This
need
isn't a flat Earth
university
idea.
knowledge.
Yeah, but this is all just mainstream information when it comes to how gas particles work.
Yeah, and
Okay.
mainstream information about gas particles says that each particle, like all other particles, get accelerated downwards.
No, it doesn't. It doesn't. It says they move at random in all directions. Do you need a citation?
I'll read it out.
Yeah,
Posted it.
thanks, Tito.
all particles have mass.
The
From
following
my end.
assumptions about the structure of the gases are made in order to investigate the statistical rule of the random motion of the molecules. The size of the molecules is negligible compared with the distance between gas molecules. Molecules collide infrequently because the collision time is much shorter than the free motion time. The effects of gravity and any other field forces are negligible, thus the molecules move along straight lines between collisions. The motion of gas molecules obey Newton's second law. The collision of gas molecules is elastic, which means that the kinetic energy before and after the collision is the same. Therefore, the gas can be viewed as a set of elastic molecules that move freely and randomly. Any gas that satisfies the above assumption is referred to as an ideal gas. At thermodynamic equilibrium, the density of the gas in a container is uniform. Therefore, it is reasonable to assume that the gas molecules do not prefer any particular direction over other directions.
Can I correct a little bit? What you said before the conclusion, I can. This is all agreeable, and the only thing, yeah, about that random movement, yeah, and kinetic energy, it's all relative. Like in a closed system of only gas particles, they do indeed move in random, because you actually can calculate. If you know all the data, which is kind of physically impossible for now, maybe forever, but for now it's random. It seems random because we cannot predict it fully. But yes, it does. In relative to each other, particles do collide and move around each other, but it's in the closed system if you look just on those particles. But there is no closed system in there. Like Earth is part of that system too. That acceleration is. So in that system, all particles do get pulled downwards. So because it's gas, because they have enough kinetic energy to not be like stuck together, they have low intermolecular forces, and because there is more energy on the surface, because if temperature on Earth, like if Earth was, for example, further away from the sun, or it was not heated that much and it was colder, that gas would probably become liquid at some temperature. So it's just the surface is warm enough to keep the particles apart, and they do move randomly in that system between each other. But like if you look at the whole system, they do get pulled downwards.
No, they don't. We can test this easily in a lab. It doesn't happen. Okay, if you get just say I have a gas pressure system in a container. Okay, and then I take the lid off the top of the container. None of the gas that is in that container is going to get held down into the container by gravity. Okay, diffusion is going to take place, and all of those gas particles are going to diffuse. Basically, they're going to blend in with the other gas particles, and everything's going to equalize. There's going to be no additional pressure left in that container. Okay, if it's a different type of gas, let's say we have an extremely heavy gas like SF6 in the container, all of the SF6 is going to be gone out of the container. Okay, even if it's a much heavier gas than the gases in the air. Like let's say we get a fish tank of and we fill it up with SF6 gas,
And you drop it for
a heavy gas. Yeah. So we come back the next day, all of that SF6 is going to be gone. Gravity's not going to hold any of that gas in the container. It's all going to blend in with the gas, and there's not going to be any additional pressure in that tank.
Well, circulations, maybe wind,
No,
whatever.
even without circulation, it's just the constant movement of the gas particles that are eventually going to cause diffusion to take place. That's what happens. You can look into it if you want.
Okay, what about like if we drop some heavy gas from 20 kilometers where there is almost no air? It
Yeah,
will fall down.
relative density will temporarily be at play, but those gas particles are still just moving in random motion. Okay,
Down.
and none of that gas. Yeah, but it's not going to stay down. It's going to diffuse with the rest of the gas.
No, it's gonna go
Yeah, but you can
down.
release exactly. So that's because it's a heavier gas. Release a lighter gas, it's going to go up.
Depends what the temperature of the gas is.
It's a great
But
point. Oh, we've
if-
got a look. Talk to Jedi about gases. He knows a bunch more than I do about it. Because I got to go on mute anyway. But I did appreciate
Okay.
talking to you, and good to see you back in the channel.
Yeah, it was very nice to hear you. I haven't heard you in months, so thank you.
Appreciate it.
So what's this about gas?
Oh no, we've had this conversation before about gas. It's all about containers, guys. I cannot hear any more of that.
Okay.
Yeah, sorry.
So he's
It has
saying
to
that
be.
gas particles get pulled down the same as anything else at 9.81 meters per second squared. That was his claim.
It's not true.
That's what I said.
You've got a vacuum chamber and a tap halfway up the vacuum chamber. When you open the tap, when the gas comes rushing in, it doesn't fill up from the bottom. The gas is moving freely and randomly in all directions because of the physical collisions it has with other gas molecules and the walls of its container. Let's say, for one instance, a gas molecule gets hit in the direction of down, and then it hits the bottom of the vacuum chamber, and if unencumbered, it's going to go straight back up again, and then it's going to hit the other wall, because gases are in constant motion. So no, gases don't fall like solid or liquid objects. Gases have got energy that's given to it by temperature. That's why they move.